Hello students, good time to all. I am Chandan Kumar Pradhan. Welcome to this channel Chandan Physics. In this video, we are going to discuss London's equation and penetration depth. Let's begin. We know about superconductivity. What is superconductivity? If we take a metal and increase its temperature, accordingly the resistance of that metal also increases. If we take its reverse process, means decrease in temperature, the resistance gradually decreases. But in some situations, at a particular temperature, the resistance suddenly decreases to 0, and that temperature is known as the critical temperature or transition temperature, at which that resistance suddenly jumps to 0, and that phenomenon is known as superconductivity. And the metals or the specimens which obey that superconductivity phenomenon is known as superconductors. And the process of superconductors we can't explain by using Maxwell's equations. Therefore, in the year of 1934, two scientists, as they are two brothers named as F. London and H. London brothers, proposed a theory. By using that theory, we can easily explain the phenomenon of superconductivity by a simple modification of Maxwell's equations. What was their theory? Superconductor is composed of normal and superconducting electrons. Two kinds of electrons are there in superconductor. One is normal electron, another one is superconducting electrons. How these two types of electrons responds to that of temperature? At superconducting temperature, the conduction is only due to that superconducting electrons, but as the temperature increases, the number of superconducting electrons decreases, while the number of normal electrons increases. As far as the temperature is concerned, on that basis of temperature, these two kinds of electrons responds. When temperature increases, superconducting electrons decreases and number of electrons, normal electrons, increases. And if temperature decreases, the superconducting electrons increases and normal electrons decreases. By taking that point, he saw how the phenomenon of superconductivity is easily explained by using a small modification of Maxwell's equations. Let we see how we use London's equations to prove the phenomenon of superconductivity. Let small m mass of electron minus E, charge on electron. Two kinds of electrons are there. One is superconducting electrons, n of s, the number of superconducting electrons per unit volume. Similarly, n of E, normal electron, sorry, that is n of n, n of n, the number of normal electrons per unit volume. V of s is the drift velocity of superconducting electrons. Superconducting electrons. And E, the electric field. Therefore, applied electric field E is equal to F by Q, force per charge or E is equal to that force, let F, charge, electronic charge minus E. Therefore, F is equal to minus E into E. That force, mass into acceleration, mass of electron, that is m, acceleration, rate of change of velocity, that velocity due to that drift velocity, d Vs of dt is equal to minus E into E. Next, for current density, for current density of superconducting electrons, superconducting electrons, that is J of S, N S E V of S, number of superconducting electrons per unit volume, charge of electron, V of S, drift velocity of superconducting electrons. We use negative sign as that direction of current density is opposite to that of drift velocity of electrons. Therefore, we use negative sign. Now, differentiating with respect to time. Now, differentiating with respect to time, we get djs by dt is equal to minus ns e dvs by dt, or djs by dt is equal to minus ns e. In place of dvs by dt, we substitute minus e by m, minus e divided by m, or djs by dt is equal to minus plus ns e square divided by m e. Which one is the first London equation? This is the first London equation. First London equation. Let me take curl on both sides. Taking curl on both sides, d by dt curl of js ns e square divided by m curl of e. From Maxwell's equation, we know, from Maxwell's equation curl of E is equal to minus del B by del T. Therefore, d by dt grad cross Js is equal to, putting that value grad cross E, minus ns e square divided by m del B by del T. Now integrating it with respect to time. Integrating with respect to time. Integrating with respect to time. So we get, as we integrate with respect to time, so dt cancel out, its integration as grad cross Js is equal to, again integrating with respect to time, del t cancel out, its integration minus ns e square divided by m into b vector. This is the another equation of London, and it is known as, this is known as second London equation. Second London equation. And by using this two London equation, we can easily explain about superconductivity. Here is a theory proposed by London brothers, and by taking that theory, we point out two equations. This is the first London equation, second one is the second London equation, and this two London equation explains the phenomenon of superconductivity, just a simple modification to Maxwell's equations. Next, London penetration depth. London penetration depth. From Meissner effect. What is Meissner effect? if we apply an external magnetic field to a normal metal, then external magnetic fields are penetrated to that of metal or conductor. But in case of semiconductor, if we apply external magnetic field, then these external magnetic fields are exploits from that semiconductor section, or we can say inside that of semiconductor there will be no such external magnetic field. External magnetic field will be 0 or magnetic flux density will be 0 inside that of superconductor. But in case of conductor, there will be magnetic flux inside that of conductor. In superconductor, no external magnetic field or magnetic flux density inside that superconductor is 0. That is the Meissner effect. But in reality, there will be some magnetic flux density inside that of superconductor, and that process is known as penetration depth, and we can explain that penetration depth by taking London's equation. Let us use Ampere's circuital law in differential form. From Ampere's circuital law in differential form, grad cross B is equal to mu naught Js, current density due to that of superconducting electrons. Take call on both sides. Taking call on both sides, grad cross B is equal to mu naught grad cross Js. Grad cross B, we use that identity, grad of grad dot B minus grad square B is equal to mu naught grad cross Js. As we know, grad dot B is equal to 0, so that term 0 minus grad square B is equal to mu naught grad cross Js, or minus grad square B is equal to, let me put the value of Js. The value of Js, grad cross Js, from that of second London equation, minus ns e square divided by m into B vector minus mu naught ns e square divided by m into B vector minus minus cancelled out. So, grad square B vector is equal to mu naught ns e square divided by m into B vector. Grad square B vector is equal to that term 1 by lambda square to B vector, where lambda, that is m divided by mu naught ns e square under root lambda, and that lambda is nothing but London penetration depth. Penetration depth. So how we show the concept of penetration depth? This is the three-dimensional differential equation. That equation number 1, three-dimensional differential equation. In one dimension, equation 1 can be written as, in one dimension we write it d square b dx square is equal to 1 by lambda square into b. This is a simple differential equation, and the solution of that type of differential equation as b is equal to b naught e to the power minus x by lambda plus b1 e to the power x by lambda, whereas b naught and b1 are constants. B naught, b1 are constants, and their values can be obtained by applying boundary conditions. Here in that of solution, the term b1 x by lambda will be 0, because the field increases as we move in that of superconductor. For that reason it will be 0. As field increases, as we move inside superconductor. Therefore the term will be 0. The only contribution is e to the power minus x by lambda, whereas x, the term x, here x, the distance from surface of the specimen, that is the distance from the surface of the specimen, and b0, that is the magnetic flux density, at the surface of superconductor, It will be three situations we can draw. If x is equal to lambda, therefore b is equal to b naught e to the power minus 1, and b is equal to b naught by e. One situation. Okay, what exactly it indicates? That expression, that is the London penetration depth. Thus we explain it, what it signifies. Thus London penetration depth is defined as the measure of the distance from the surface of the superconductor at which the magnetic of decays to 1 by E of its value at the surface of the superconductor. If we plot the graph in between the distance x to that of magnetic field B, then it will be gradually decreases exponentially, and here the B0 divided by E, that will be the penetration depth at a specific distance lambda. So, London penetration depth is defined as the measure of the distance from the surface of the superconductor at which the magnetic of decays to 1 by E of that original value the surface of the superconductor. This is a first situation when x is equal to lambda. If x is much less than lambda, then what happened? At that of situation x by lambda is nearly equal to 0, therefore B is nearly equal to B naught. B is nearly equal to B naught, and we draw our conclusion. Magnetic flux density everywhere inside the superconductor is constant and equal to the value at the surface of superconductor. B is equal to B naught. Magnetic flux density everywhere inside the superconductor is constant and equal to the value of the surface of that of superconductor. Next observation, if x is very greater than lambda, then what happened? We say x by lambda is nearly equal to infinity, therefore B is equal to B naught to e to the power minus infinity, therefore B is equal to B nearly equal to 0, as B to the power minus x by lambda as infinity minus infinity 0, so B is nearly equal to 0. What it indicates? Thus the magnetic flux density inside that of sample is 0. Magnetic flux density inside that sample or inside that specimen which was given to us will 0. That is the Meissner effect or the perfect diamagnetism condition. In this way, London effect explains flux penetration as well as Meissner effect. It is Meissner effect and that one is the London penetration depth. So, here we observe what is London penetration depth. By taking London equation, we show what is London penetration depth. Mathematically, we show the physical significance of all the situations. Here, with the help of this video lecture, we understand the concept of London equation and penetration depth. What was the theory proposed by two London brothers, and mathematically we derive first London equation and second London equation, and then London penetration depth by using London's equation. In various situations, we obtained from that particular given equation and all the physical aspects of these equations. So, with this useful and informative notes, let me wind up this session. Thank you.